Everyone, this is Sahu from Lund Research Center of our Technology, Sweden, AB. I'm very happy to have this opportunity to present our work titled Approximate Noise-Whitening in MIMO Detection via Banded Inverse Extension. This work is co-authored with my colleague Wang. We start with a brief review of BIE history. So it has been known that for more than 30 years that under the moment constraint, the first and second moment constraint, the maximum entropy is attained with a complex valued Gaussian distribution. Later, this problem has also been extended to the constraint that the covariance matrix equals to R, but R only equals to C inside the banded region that comprises the middle 2 times nu plus the main diagonals, where nu is the parameter specifying the size of the band. While the remaining entries outside this band can be arbitrary. Surprisingly, the maximum entropy distribution is still Gaussian, and the unique solution R, whose inverse is nu banded, is called the BIE of C. While the nu banded means that for a squared matrix R, its entries other than those located on the middle 2 plus the main diagonals are all zeros. Later in 2000, Karvik and Morov has shown a least method to compute the BIE in the following. And you see from here, it is very simple. Only inverses of principal submatrices are needed, which are of sizes nu plus 1 times nu plus 1. So it becomes extremely simple if setting nu equals to 1, which are only two inverses of 2 times 2 matrices. Also, let's see here, only the entries in the banded area of C are used, while those entries outside this banded can be discarded from memory storage. With BIE briefly introduced, next we can see that these conventional methods for approximate matrix inverse. And in most literatures, these approximate inverse methods are based on Human series or its variants. So it will have some formulation like this. Instead of inverting C, some simple matrix R can be inverted. And through this series, the approximation of inverse of C can be obtained. However, there are also two main drawbacks from these conventional methods. The first one is that in general, it needs quite a few terms to converge for satisfying accuracy. But the complexities of matrix applications in the series are also very heavy. Then the second drawback is that in most literatures, the accuracies are measured from approximation errors, which, however, does not reflect the final impact on the detection performance, such as in a practical memory system we'll consider. Then, before introducing our method, now ask the question why we would like to approximate the Noise-Whitening. Well, unlike most literatures, while the main assumption for approximated inverse is that the matrix to be inverted has large sizes, such as in massive MIMO, here in our problem, this assumption is not necessary. This is because that even a G-Load-B or base station is equipped with a massive MIMO antenna array. A UE is only typically equipped with a few antennas, such as 4 or 8. Since the number of layers supported in the MIMO transmission cannot be higher than the number of receiving antennas, the effective MIMO channel and also the noise covariance matrix are not with very large sizes. Even though saving a few operations via approximate noise-whitening on each resource element is still meaningful when considering the overall savings of the entire subframe. This is so because noise-whitening is implemented on each of the RE. For example, in an OFDM system that comprises 4,096 subcarriers and 14 OFDM symbols in a subframe, in total there are more than 57 resource elements, and the operations for memory detection and the noise-whitening can be implemented on. Therefore, even saving a few operations on each RE, the total amount of saving is still quite massive. Before talking about noise-whitening, we would like to show some general preprocessing with MIMO detection, as shown in this diagram. So what typically a MIMO detector does is that first it will whiten the noise on the received data of Y. Afterwards, a matched filter is applied, followed by pre-filtering. Then the MIMO detection will be implemented on the effective received singular model, which is shown here. And the different pre-filters R can be designed. And that will depends on the MIMO detectors, whether it is linear or non-linear. Taking the minimal mean square error QL decomposition-based detectors as an example, in these cases, the effective channel for the MIMO detection F is set to R, while R follows this QR decomposition, which also contains this noise whitening. And what is important here is that this diagram actually represents a wide range of linear and nonlinear MIMO detectors, as explained in our papers. And you see here, noise whitening is an inevitable operation that will be needed for all the MIMO detectors. Therefore, how to simplify the inversion of C is of our interest. And then why would we like to apply this BIE method? Well, as we show in the paper, it turns out that the BIE-based approximate noise whitening is very promising because it's optimal from two completely different perspectives. The first one is that the BIE-based inverse is actually minimize the noise distortion measured from the KL divergency. Then what's more important is that the BIE-based inverse also maximizes the GMI, generalized mutual information, which is a K metric for measuring the final MIMO detection performance, which is more important. So here we start with the definition of GMI. To elevate the GMI, we can assume that we approximate the inverse of noise covariance matrix C and arbitrary matrix T. In this case, the conditional PDF on which the MIMO detector will operate on is reached the following. While the original exact PDF is here, so as you see, the only difference is that the inverse of C has been replaced by arbitrary inverse or arbitrary matrix T. Then the GMI is defined in the following, which can be computed directly. As you see here, this GMI is actually measures the detection performance on this so-called mismatched detection model P tilde, which is different from the original metric noise covariance matrix C. And in this paper, we have shown in proposition 1 that the GMI can actually be derived in a very simple closed form. And from here, it's worth noting that if one sets this T equals to the exact inverse of C, then the GMI actually coincides with the true MIMO capacity. Whereas if you set in T equals to identity matrix, then the gap between GMI and the MIMO capacity actually shows the rate losses in the mismatched MIMO detection by treating the colored noise as white. Therefore, from this sense, GMI actually bears practical meanings and can reflect the effectiveness of an arbitrary approximate inverse T. So what one can do is that trying to optimize this matrix T, given the constraint that it is banded. However, this optimization is not very simple. Therefore, we continue with this high-SNR simplification, in which cases the GMI can be approximated in the following, so it's simpler than before. And if we take the first order derivative directly with respect to the non-zero elements in matrix T, meaning inside the banded area of T, and letting them equals to 0, it shows this. So what you see from here is that, so first of all, we know that we can constrain this matrix T to be banded. Then secondly, from here, it shows that the inverse of T equals to the original covariance matrix C inside this banded region, specified by the parameters U. So from the definition before, this is exactly the definition of the BIE of original noise covariance matrix C. So what this tells us, this shows that the BIE-based noise whitening is also optimal or asymptotically in SNR when maximizing the GMI. So this is also a very important motivation for us to use this BIE. Then the other reason is that if we consider special case, which is a Gauss Markov process, then the BIE-based inverse actually can be exact. This is so since we can see that from here that if we define two vectors x and zeta and consider a first order and the variance stationary GMP process like this, then it can be shown that the inverse of the covariance matrix C originates from this GMP process. It is already one-banded. One-banded meaning that only the main diagonal and the first upper and lower diagonals can be non-zero. Therefore, if one uses a BIE with setting E equals to 1 to approximate the inverse of C, there will be no losses at all. Therefore, for GMP processes, the BIE-based approximated inverse is exact. This is also an important motivation for us to apply this BIE, because in many cases, such as modeling the spatial correlation of the MIMO channel, they're close to a GMP process. In the paper, we have also discussed a few potential improvements for the BIE in 3 different directions. The first one is that one can apply this gradient descent search to further improve the BIE by initializing the matrix T with the closed form solution obtained from the High-SNR approximation, which is just the BIE of the original covariance matrix C. And the second improvement is to optimize permutation matrix of the original matrix C to be inverted. One can do it in an optimal way to maximize the GMI to find the 2 different permutation matrices, but this could also be a little bit complex. And a heuristic approach we found it is effective is to just find the permutation matrix P and Q such that the energy of C will become more concentrated in the banded area. This is so because then the truncation error from C to a banded simplification of C would have smaller truncation errors. Then the third potential improvement is to apply some additional terms in the Newman series, for example. With one additional term, it can be computed that the approximation of the inverse of C can equals to this form. So the accuracy can be further improved. However, as you see, the list also some additional matrix multiplication, which can be also complex. Further on, there will also need some refinements to make the inverse to be still positive definite when it's necessary. All right, then we show some simulation results. We first consider GMI for 4x4 MIMO. In these cases, we can extract a general covariance matrix C in the following. So it's close to a GMP process. However, it contains 2 different variables, beta and alpha. And actually, the ratio between beta and alpha measures how far away this matrix C from the GMP. When beta equals to alpha, then the C is equal to a GMP process. But if the difference between beta and alpha becomes larger, then C is more diverted from a GMP process, and the BMI can be less effective. So in the figure that we inverted this C by setting beta equals to 1.5 alpha, so it is away from GMP processes, and we evaluated different values of alpha and 4x4 relay MIMO channels. So as we see here, when alpha is small, the rate losses of GMI compared to other conventional methods, such as this diagonal method, which is red curve, and also the block diagonal method, which is the green curve, and also our BME method. All of them are very close, and GMI losses are negligible. This is because in this case, when alpha is small, the C is almost the diagonal dominant. However, when the value of alpha increases, as we see that, the BIE is superior to the conventional methods, especially if we, with permutation, then when alpha is not is equals to 0.7, we see that the permutation actually helps a lot. And further on with one additional term, we can see that the BIE is very close to the GMI obtained with the exact inverse, meaning the apple bound. So this shows that actually the BIE is quite effective, especially if cooperating with permutation. Also, one additional terms. Except for GMI, we also measured the mean square errors, two different types of mean square errors. The purpose of the first type of mean square errors, aka MSE, is actually to measure or normalize the difference between the approximate inverse and the exact ones. While the second type of MSE, trying to measure the difference between the effective noise covariance matrix after noise whitening to an identity matrix, meaning the perfect noise whitening. So it measures how far away the noise is from white. Although these two types of MSEs do not transfer directly into the impact on the final GMIs, they somehow also reflect how close the approximate inverse are to the exact ones. As we see from these CDF curves, we see that the BIE-based inverse is also superior to the block diagonal approximations. In addition, if we can have permutation and further with one additional terms, the MSE are very, very small. Okay, in the last, we also show this the GMI and the 8x8 MIMO system. In these cases, we actually generated a noise covariance matrix with spatial correlation, and we test and the medium correlation. As we see from here, that the BIE also performs quite good, and also with one permutation, without any additional terms in these cases, is quite close to the upper bound. So all of these simulation results show that the BIE actually is quite robust and also effective in approximating the noise whitening covariance matrix, and especially if we consider the final detection, MIMO detection performance in terms of GMI. So to summarize, the takeaways are the following. So first, we show our motivation and benefit by applying the BIE in approximate noise whitening, which is threefold. First one is it's least noise distortion. The second is this asymptotically maximizing the GMI for the mismatched MIMO detection model. And the last one is that it is exact when matrix C to be inverted or ranges from GMP. So actually, not only for noise whitening, the same principle of this BIE-based approximate inverse can be applied to any other MIMO problems that as long as the matrix inverse is involved in. And then also in this paper, we have developed a GMI-based information theoretical tool to assess the final impact from the approximation errors on the final MIMO detection performance. And this information theoretical tool can also be applied for any other methods to measure how good the approximation method would be. And we also proposed some potential improvement, including gradient descent search permutations and additional terms in the Newman series. And compared to conventional methods, we have shown that the BIE is very robust, and also it can provide substantial gains, both in increasing the GMI and also reducing the MSEs. Okay, thanks a lot for listening. And if anyone any questions, you're more than welcome to contact me.